Hi! Today we will review the complementary metal oxide semiconductor, also known as CMOS, where we will be focusing on the fabrication of CMOS using Analogue. The group members for this project are Afika, Najat, and Amir. Moving on, the contents that will be covered today include CMOS introduction. Next is CMOS fabrication method. And lastly, fabrication of CMOS using Analogue.
CMOS introduction. CMOS, or complementary metal oxide semiconductor, is a combination of NMOS and PMOS transistors. NMOS is an N-type metal oxide semiconductor, and PMOS is a P-type metal oxide semiconductor. N-type is a type of pentavalent impurities, and P-type is a type of trivalent impurities doped on the semiconductor. For less power dissipation requirement, CMOS technology is used for implementing transistors. CMOS fabrication methods. Fabrication of CMOS transistors as ICs can be done in three different methods. 1. The NWEL/PWEL technology. NMOS and PMOS transistor are developed over the wafer by simultaneous diffusion over an epitaxial growth base, rather than a substrate. 2. The twin-well technology. NMOS and PMOS transistor are developed over the wafer by simultaneous diffusion over an epitaxial growth base, rather than a substrate. 3. The silicon-on-insulator process. An insulator material is used rather than using silicon as the substrate to improve speed and latch-up susceptibility. Fabrication of CMOS using NWEL. Step 1. First, we choose a substrate as a base for fabrication. For NWEL, a P-type silicon substrate is selected. Step 2. Oxidation. The selective diffusion of N-type impurities is accomplished using silicon oxide as a barrier which protects portions of the wafer against contamination of the substrate. Silicon oxide is laid out by oxidation process done exposing the substrate to high-quality oxygen and hydrogen in an oxidation chamber at approximately 1000 degrees Celsius. Step 3. Growing of photoresist. At this stage, to permit the selective etching, the silicon oxide layer is subjected to the photolithography process. In this process, the wafer is coated with a uniform film of a photosensitive emulsion. Step 4. Masking. This step is the continuation of the photolithography process. In this step, a desired pattern of openness is made using a stencil. This stencil is used as a mask over the photoresist. The substrate is now exposed to UV rays. The photoresist present under the exposed regions of mask gets polymerized. Step 5. Removal of unexposed photoresist. The mask is removed and the unexposed region of photoresist is dissolved by developing wafer using a chemical such as trichloroethylene. Step 6. Etching. The wafer is immersed in an etching solution of hydrofluoric acid, which removes the oxide from the areas through which dopants are to be diffused. Step 7. Removal of whole photoresist layer. During the etching process, those portions of silicon oxide which are protected by the photoresist layer are not affected. The photoresist mask is now stripped off with a chemical solvent, hot sulfuric acid. Step 8. Formation of NWEL. The N-type impurities are diffused into the P-type substrate through the exposed region, thus forming an NWEL. Step 9. Removal of silicon oxide. The layer of silicon oxide is now removed by using hydrofluoric acid. Step 10. Deposition of polysilicon. Polysilicon is used for formation of the gate because it can withstand the high temperature greater than 8000 degrees Celsius when a wafer is subjected to annealing methods for formation of source and drain. Polysilicon is deposited by using chemical deposition process over a thin layer of gate oxide, which prevents further doping under the gate region. Step 11. Formation of gate region. The remaining portion of polysilicon is stripped off except for the two regions for the formation of NMOS and PMOS transistors. Step 12. Oxidation. A thin layer of oxide is produced by forcing an oxidizing agent to diffuse into the material at high temperature, forming silicon dioxide. This oxide layer acts as a shield for further diffusion and metallization processes. Step 13. Masking and diffusion. Making regions for diffusion of N-type impurities using masking process. Small gaps are made. Using diffusion process, 3N+ regions are developed for the formation of terminals of NMOS. Step 14. Removal of oxide. Strip off oxide layer. Step 15, P-type diffusion. Similar to the N-type diffusion, for forming the terminals of PMOS, P-type diffusion are carried out. Step 16, laying of thick field oxide. Before forming the metal terminals, a thick field oxide is laid out to form a protective layer for the regions of the wafer where no terminals are required. Step 17, metallization. This step is used for the formation of metal terminals which can provide interconnections. Aluminum is spread on the whole wafer. Step 18, removal of excess metal. The excess metal is removed from the wafer. Step 19, formation of terminals. In the gaps formed after removal of excess metal, terminals are formed for the interconnections. Step 20, assigning the terminal names. Names are assigned to the terminals of NMOS and PMOS transistors.
We have reached the end of the CMOS review. Thank you for listening.